Well, hello there. Let's talk about something truly amazing. Systems analysis. It sounds complicated, but consider this. Everything around us is a system. Your bicycle is a system of gears, wheels, pedals. A plant is a system of roots, stems, leaves working together to catch sunlight. A business is also a system, with people, processes, technology all interconnected. Systems analysis is simply the science of understanding these systems, especially in business, so we can make them better. It's like being a detective for a company. You look for clues, figure out what's not working as well as it could, and then come up with a plan to improve it. Imagine a pizza shop. The system includes taking orders, making the pizzas, delivering them. If customers are complaining that their pizzas are always cold, a systems analyst would investigate. They wouldn't just guess the problem, they would study the entire process. How long does it take to get an order from the phone to the kitchen? How many pizzas can the oven bake at once? How do drivers decide which deliveries to make first? By studying each part of this pizza-making system, the analyst can pinpoint the exact cause of the problem. It's a methodical, scientific way to solve business puzzles. Systems analysis is all about the what and the why. What is the system supposed to do? Why isn't it doing it perfectly? It's the process of studying a business problem or an opportunity and then figuring out what needs to be done to fix it or take advantage of it. The goal is to recommend improvements. These improvements often involve technology like a new software program, but they don't have to. Sometimes, the best solution is simply changing the way people do their work. The key is that we don't jump to conclusions. We observe, we measure, we analyze, and then we recommend. Science. So, in a nutshell, systems analysis is the discipline of breaking down a big, complex business problem into smaller, understandable pieces. It's about understanding the current situation, identifying its strengths and weaknesses, and then defining the requirements for a better future state. Think of it as creating a blueprint for success. Now, you might hear people talk about systems analysis and systems design together. That's because they are partners in problem solving. They are two distinct phases, but they work hand in hand to create amazing solutions. Think of it this way. Systems analysis is about understanding the problem, while systems design is about figuring out how to solve it. Analysis is the what, and design is the how. So, the analyst is like an architect who talks to the family to understand their needs for a new house. They ask questions like, how many bedrooms do you need? Do you want a big kitchen? Do you need a home office? The analyst creates the floor plan and specifies all the features the house must have. The systems designer, on the other hand, is like the construction engineer who looks at that floor plan and figures out how to build it. They decide on the type of foundation, the materials for the walls, and the specific wiring needed for the electrical outlets. One defines the vision, the other makes it a reality. Every great scientific investigation starts with a question. In systems analysis, it starts with defining the scope. This is the very first phase, and it's incredibly important. The scope definition phase is all about drawing a boundary around the problem. It answers the question, what part of the business are we going to study? If you don't define your scope, you could end up trying to solve every problem in the entire company at once, which is like trying to boil the ocean. It's just not possible. We need to focus our analytical energy on a specific manageable area. The purpose of this phase is to create a project charter. High-level managers, executives, senior systems analysts. The managers identify a problem or an opportunity. Sales are down. Our competitors have a new app. The analyst then works with them to investigate it just enough to define the problem and its limits. Input, that initial problem statement. Output, project scope. Output, objectives. Output, budget. Output, timeline. It sets the rules for the game we're about to play. Now we have a clear target. Once we've drawn our circle around the problem with scope definition, it's time to zoom in with the problem analysis, requirements analysis phases. These two often happen together. Problem analysis is all about understanding the current system, the as-is system, in great detail. We want to know its ins and outs, its good parts, its bad parts. The goal is to identify the root causes of the problems, not just the symptoms. A symptom might be invoices are sent late, but the root cause might be data has to be manually entered into 3 different spreadsheets, which is slow and causes errors. Here we shift our focus from the old system to the new one. We ask, what must the new system do? This is where we define the business requirements for the to-be system. A requirement is a statement of what the system must do or a characteristic it must have. For example, a requirement might be, the system must allow customers to track their order status online. The system must generate a sales report every morning by 9 a.m. We are building our wish list for the new, improved system. The participants are again the analysts and the business users. The cashiers, the accountants, the warehouse workers, they are the experts. The main technique is called requirements discovery, which involves gathering information through interviews, questionnaires, observation. The input is the understanding of the problems we gained from the problem analysis phase. The output is a requirement statement, a formal document that lists all the requirements in a clear, measurable way. Functional requirements, non-functional requirements. This document is the master guide for the rest of the project. Getting the requirements right is everything. If you miss a requirement here, the final system won't do what the users need it to do. Okay, so with our requirements in hand, we move into the logical design phase. This phase is still part of systems analysis. It's all about creating a model of the new system without getting bogged down in technical details. It's a technology-independent design. We're not talking about specific software or hardware yet. Instead, we're drawing a conceptual blueprint. We might create diagrams showing how data will flow through the new system, or models of the information the system needs to store. It's kinda like designing the layout of a new kitchen. You decide where the sink will go, the stove, and the refrigerator for the best workflow. All that before you pick specific brands and models. The purpose of logical design is to translate the business requirements into a structured model. That model is what system designers will use to build the physical system. These could be data flow diagrams, entity relationship diagrams, or use case models. These models act as a universal language. They help business users and technical developers get on the same page. After one or several logical models, we enter decision analysis. Here we evaluate options. The purpose is to identify candidate solutions, analyze feasibility, and recommend the best one to management. The analyst presents findings. Based on our study, here are ways to solve the problem, and here is the best choice. Option A, buy a prepackaged software solution. Option B, build a custom system from scratch. Option C, tweak the existing process without new technology. For each option, the analyst evaluates feasibility. Is it technically possible? Is it operationally acceptable? Is it economically smart? The output is a formal recommendation. The final decision is made by management. This phase concludes the analysis journey and paves the way for design and implementation to begin. There isn't just one way to do systems analysis. Just like a scientist might use different tools for different experiments, a systems analyst has several approaches they can use. These are like different recipes for studying and modeling a system. One of the classic methods is called structured analysis. Think of it as the divide and conquer approach. It focuses on processes. It uses data flow diagrams or DFDs to show how data moves through a system, where it comes from, how it's transformed, and where it ends up. It breaks a large, complex system into smaller, manageable processes. Another powerful approach is called information engineering, or IE. This method puts data first. The data a business uses, customer information, product details, orders, is the most stable part of the business. The processes might change, but core data usually doesn't. IE builds a detailed model of the organization's data first. Tools like entity relationship diagrams or ERDs are used. Once the data model is solid, processes are designed around it. Then there's object-oriented analysis, or OOA. It treats a system as a collection of objects. An object combines data and the processes that act on it. For example, in a pizza shop, a customer object holds data like name, address, phone number, and methods like place an order or update an address. OOA mirrors the real world and makes reusable components easier to build. That saves time and effort long term. All these approaches use models to solve problems. Models are simplified representations of reality. They help us visualize and understand complex systems. They let analysts, users, and designers communicate clearly about structure and behavior. Sometimes the traditional step-by-step analysis process can take a long time. In the fast-paced world of business, we sometimes need answers more quickly. That's where accelerated methods come in. These are like shortcuts in our scientific process, designed to deliver solutions faster. One of the most famous is prototyping. Instead of spending months on a requirements document, the analyst quickly builds a working prototype. The prototype might not be fully functional, but it gives users something they can see, touch, and interact with. It's like building a cardboard model of a house before building the real thing. Prototyping helps users figure out what they really want. People often struggle to describe requirements abstractly. When they see a prototype, they might say, "Oh, I like that button, can we move it?" Or, "This screen is confusing, simplify it." That feedback loop lets the analyst refine the system quickly. Main pro speed, main pro better user engagement, con can lead to quick and dirty solutions if unmanaged. Con, users may assume the prototype is the final system. Now we have to ask a very important scientific question: is this even a good idea? This is called a feasibility analysis. It's a reality check before we commit a lot of time and money. There are 4 main types of feasibility that we need to consider. First, there's technical feasibility. This asks the question, can we actually build it? Do we have the technology, the tools, and the expertise to create this solution? Second is operational feasibility. This is about the people. It asks, if we build it, will they use it? And will it work in our company's environment? Third, we have economic feasibility, also known as a cost-benefit analysis. This is the money question. Is it worth the cost? Finally, there's schedule feasibility. This one is simple. Can we build it in the time allotted? A feasible project is one that passes all 4 of these tests. Technically possible, operationally sound, economically wise, and can be done on time. So, after all this investigation, modeling, and feasibility checking, what happens? The systems analyst's job culminates in comparing the different candidate solutions and making a recommendation. Imagine we have 3 options for our pizza shop. Buy an off-the-shelf ordering system, build a custom one, or just hire more staff to handle phone calls. The analyst would create a comparison matrix. This is a chart that scores each option against a set of criteria, such as cost benefits and how well it meets the key requirements we identified earlier. It's a scientific way to compare apples to oranges. The analyst doesn't just present the numbers, they tell a story. They explain the pros and cons of each alternative in clear business terms. Option A, the off-the-shelf software, is cheapest and fastest to implement, but it only meets 70% of our specific requirements. Option B, building a custom system, is more expensive and will take longer, but it will be a perfect fit for our unique workflow and give us a competitive advantage. This allows management to make an informed, evidence-based decision, not just a gut-feeling guess. Ultimately, systems analysis is the brain behind smart business solutions. It's the disciplined, scientific process that prevents companies from wasting millions of dollars on technology that doesn't work or doesn't solve the right problem. It bridges the gap between the business people who have the problems and the technology people who build the solutions. By insisting on a thorough understanding of the problem before jumping to a solution, systems analysis ensures that we build the right system and we build the system right. It's about being methodical, being curious, and using our brains to make things better. From defining the scope to analyzing problems, gathering requirements, and recommending a feasible solution, systems analysis provides a roadmap for improvement. It transforms vague complaints like, "Our process is too slow," into a concrete plan for a faster, more efficient, and more successful future.